Yeah, actually, on a normal day, if someone would have asked me the question, what are the theoretical concerns of molecular dynamics, I would have just one answer, as she said, you run it on the largest supercomputers in the world and all your concerns are gone. So, but it's one has to think about it. So I think it's a good bunch of people. It's a good topic to talk about in terms of what sort of problems are there in molecular dynamics as we practice the simulations. I presume a lot of us, almost everyone here, are doing molecular dynamic simulations. And what sort of things are something that concerns us? It's very difficult actually, because whatever is done theoretically in terms of the underlying theoretical statistical mechanics and whatever is happening in front of us in a molecular dynamic simulation, between them, a huge number of steps have gone through. And it's very difficult to connect step by step where has actually some error come in. So I will try to talk about a few errors which are not errors, I would say a few considerations which are more theoretical, and then they would get borderline into implementational. And I would like to speak more on the implementational aspects of things, because I believe that's where, because at the end of the day, what happens is when you start doing a molecular dynamic simulations, let's say from an applications perspective, not necessarily from a developmental perspective. You start doing molecular dynamic simulations, some interesting observation is made in terms of some collective motions of atoms moving together. You have two options. One option is to, of course, characterize that even better, quantify, but quantify doesn't mean too much, because at the end of the day, you're just finding some numerical attributes to whatever you're seeing in front of you. Might be you're getting some thermodynamic or kinetic parameters, but you're seeing some stuff. More often than not, what you end up doing is you end up going back to the literature and asking the question, has some experimentally seen this or not? Or is there some sort of experimental connection to this? Is there some sort of qualitative experimental connection to this? And then you see that might be there's some residues that are important, and then you come back and see in your simulation that these residues are doing something cool, and you try to make a story out of it. Of course, that's where the often a lot of biophysics-oriented, biology-oriented papers, I would say, would be published in that way. How statistically significant those kind of observations are, I think those are equally important. And I think that's what I was trying to get at today, is how statistically significant is an observation in a molecular dynamic simulation, and what might be the places where an observation that might be very, very interesting but might be not as statistically significant come into the picture. But the problem remains, it's very difficult to remove these kind of separate between these two kind of observations, something that is statistically significant and something that is biologically relevant. It's very difficult to kind of find that observation which is both. So let's start then. That's why I didn't even have a first slide. I just wanted to kind of give you a feeling of what this thing is. So molecular dynamics, as we all know, is a very, very simple thing. We are solving Newton's laws of motion. We have the chemistry in terms of we have atoms. The atoms have normally electron clouds. We're assuming that these are nothing but springs. So we are approximating the electron localization as springs. Not only springs, but additive springs. Two major approximations have been made. And then with those, we start solving Newton's laws of equation, force equals to mass times acceleration. And we hope that during the simulation, atoms would move in a way that they would get to a certain potential energy minimum. So let's start from that equation actually. So, here is a fancy movie, like we have seen this many times, like the protein folding. Start from one state, which is the energy, the potential energy, which is quite high, and then the protein starts folding, and you can do this on supercomputers. It's extremely parallelizable. In fact, a very simple theory. So, as far as the theory is concerned, it's a quite correct theory. Like let's think of the only other thing that comes in mind is density function theory. But the theory, at the level of theory, if you consider the energy as a functional of density, it's perfect. You can write equations. When you go to implementing that theory, that's where a lot of assumptions come in, a lot of considerations come in. So at the level of theory, it's like the oldest possible theory available today. Okay, so now you numerically discretize this, and let's just take this equation, as is, like change the position as a function of forces. In fact, the forces are nothing but derivatives of an atomic potential. So if you simply take this equation and solve this equation, then at infinite time, so to speak, what you will see is you get a distribution that looks like that looks like this. It's basically a delta function with some sort of a degeneracy term in it. So this equation, therefore, is so let's do an experiment where in our molecular dynamics simulations we just turn off temperature for a time, which is just do minimization, energy minimization. So let's do MD with temperature 0. What you'll end up getting is, if you really learn long enough, you'll get what you call a microcanonical ensemble. So where the structure will always reach the bottom of the potential that is being created, and that will be the most probable form of the structure. Beyond that, so it's like a delta function. So all the structures will just be stuck in one particular valley. Odds are this valley is like, so delta is a canonical delta function, and like let's say E of I is E of beta is the lowest possible energy that this sum of potentials is going to give you. So the structures are going to evolve following that equation, and they will go to the bottom of the potential and just stay stuck. So this is you will get a potential energy minimum structure. This is deterministic. You do it as many times as you want to, you will end up getting the same structure again and again. So this is what you will. This is the way you will represent an isolated system or an NVE ensemble in molecular dynamics. Now, of course, this delta is very sharp. For practical considerations, it doesn't remain like a sharp function. You actually still get a bit of a distribution due to the finite size of the system that is being simulated. That's one of the issues that I bring in. So, anyways, the most uninteresting ensemble in terms of biology is concerned. So, as I was telling that we have the system, we have the surroundings, and in an isolated system, there is no communication between the system and the surroundings, and that's where you get a distribution, which is a delta function-like distribution. However, a lot of living systems are actually, we sustain, we live because we are like reactors. There's energy influx, energy outflux, and we do work between that energy influx minus energy outflux. So the other statistical mechanical ensembles that represent this sort of a system are I would say closed systems and open systems. So canonical and grand canonical ensembles, where in the closed system, between the system and the surrounding, you actually have some exchange of heat, and in the open system, you have both matter and heat being exchanged. For today's discussions, let's focus on the canonical ensembles, the place where heat is being exchanged between the system and the surrounding. Let's not think of particles. Particles indeed can exchange, and there have been theoretical work in doing that. But for most of molecular dynamics simulations today, what we end up thriving for is to get very good ensembles for closed systems, which are otherwise called canonical ensembles. So these are like NVT or NVT kind of ensembles. And here, the distributions are different. We all know it's a Boltzmann distribution. And so, the probability is proportional to the energy of a system in a particular state. And now, of course, we are seeing weirdly, temperature has come into play. In the previous case, in a microcanonical ensemble, there was no temperature. There was no concept of temperature, actually. Now, we have a distribution that depends on temperature. So, where does temperature come from? Is a question then. So, okay. In fact, let's not get into where does temperature come from. So, temperature comes from how do you get a distribution? So, anyone wants to answer? How do we get distributions in statistical mechanics? Let's say, how did we first learn that this is a Boltzmann distribution? What was the mathematical procedure that was used? Oliver won't answer, everyone else. So, I think that there are various ways in which you can do that. The one that I really like comes from entropy maximization. So you have a particular definition of entropy called Jane's definition, which is integral over the phase space rho log rho. And then what you do is you maximize this entropy. So entropy is nothing but a measure of uncertainty. You want to find a distribution. You want to know that what is the way in which a particular variable is distributed. How will you do that? You define a Lagrangian which says that this is a function, this is called entropy. I want to maximize my entropy, I want to maximize my uncertainty under the constraints that I know something. What are the things that you know? The first thing that you know is that the probability that you get is normalized. So when you simply put in your Lagrangian, the probability, the the normalization as a constraint, you will get a microcanonical ensemble. The next thing that you can do is, in your Jane's entropy maximization tool, you would say, I want to maximize my entropy under the constraint that not only the probability is constant, but on an average, the energy